Hello and welcome. In this video I'll be covering all of the solutions for the Chapter 4 test review. So let's go ahead and jump right on in. First question wants us to express a logarithm as a sum difference or multiple of logarithms. So with one like this we would go ahead and look at any look for any multiplication or division and turn it into addition or subtraction. In this case I do have multiplication on the inside, so I should be able to separate that into two logarithms, both with the original power still intact, so a power of 1 on the x and a power of 2 on the x minus 1. But again, the multiplication has now turned into addition. At this point I should be able to take this exponent that's on the second one and move it out as a coefficient to arrive at my final result of the natural log of x plus 2 times the natural log of x minus 1. For part B, look for the ability to potentially rewrite a radical. In this case I can say that the radical is the same as a 1/2 power like so. So that 1/2 power should be able to, just like we did with the power of 2 before, I should be able to move it in front as a coefficient and say that this is really a 1/2 natural log of that x cubed times x plus 1 over an x squared minus 2. Looking for products and quotients to be able to separate. The 1/2 is a coefficient in front of everything, so I'll have to remember to group it. And in this case I've got the natural log of x cubed that's going to get to add with the natural log of x plus 1 because there's multiplication. And then I'll subtract the natural log of the x squared minus 2 because that's what we're dividing by. So at this point I should be able to move, it looks like just one coefficient in front. This power of 3 will get to move in front. And I'll go ahead and leave that 1/2 in front. If we wanted to distribute it through, that would be fine, but with this I'll just leave it in this format for my final result. Be careful with this last one, that power of 2 on the x there, since it's only on the x, it's not on the entire inside. I can't move that coefficient in front because of that subtract by 2 on the inside. Moving on now to number 2. These ones want us to take multiple logarithms and turn it into a single logarithm. So we kind of work the exact reverse of what we just did on the previous problems. So this first one, it looks like I can move the 2 up as an exponent, and then the second one I can move the 1/2 up as an exponent. So this would be able to be rewritten as the natural log of x squared minus the natural log of, and since that's a 1/2 power, I'll go ahead and write it in radical form. And since there's subtraction in between, I should be able to turn this into a quotient where x squared is being divided by then that square root of x plus 1. And there we have it. Second one, very similar. Move my 3 up as an exponent, my 2 up as an exponent, and my 4. So I can rewrite this as the natural log of x cubed plus the natural log of y squared, and then minus the natural log of z to the 4th. So the 2 that are adding should be able to be multiplying in our numerator once I combine and make this one single logarithm. So I've got x cubed times y squared, and then the minus sign will be division, so I'll divide by z to the 4th. And that's really as good as I can make that one as well. Now on to number 3, which wants us to actually just solve equations for a variable. So looks like this first one, if I just look at what I have an exponential equaling another exponential. try and rewrite this where they have the same base on both sides. So since 8 is the same as 2 cubed, I really could say that that's really like 2 cubed being raised to a power of x minus 2, which I can then rewrite as, since it's a power 2 of power, I could distribute the 3 through, so I could say that's 3x minus 6. So ultimately at this point I would be able to, since the bases are the same, just set the exponents equal to each other. So my actual expression for this one is going to be x equaling 3x minus 6. And now just do the normal algebra to try and get x by itself. So first move my 3x over, which would give me negative 2x equaling negative 6. And then divide by the negative 2 to arrive at my final answer of x equals positive 3. For part B, I have two logarithms separated by subtraction. I don't see any coefficients in front to worry about moving, so just like we did in one of the earlier parts for question 2, I should be able to rewrite this now as a quotient, because subtraction between two logs can turn into a single log with division inside. And ultimately from here, now I could do a exponentiating of both sides, raise both sides, or make each side be an exponent on the base e, because the natural log has base e. And if I were to do that, now the e and the natural log would cancel out, leaving me 2x over the 3x minus 1. Again, because those cancel out. And then e to the 0, that would just equal 1. So to solve an expression like this, I would just want to clear my fractions, so I'd multiply both sides by the denominator I have, so 3x minus 1, which then gives me 2x is equal to 3x minus 1. And subtract my 3x over, which gives me a negative x equaling a negative 1, which then is going to give me an x equals positive 1. Now with this, we'll do a quick double check. Since logarithms do have a domain restriction, just make sure that when I plug 1 in to the insides, 2 times 1 is positive still, so that should be fine. 3 times 1 take away 1, that's also still positive. So it seems as though that is okay for my final result, so we'll go ahead and commit to it. If we go ahead and move on to part C on this one, first thing I'd want to do is try and isolate the exponential, since I don't have an exponential on both sides. It's not quite the same as what letter A was, so I would just add my 5 first, which gives me 4e to the power of 2x minus 3 is now equal to positive 5. Should be able to divide the 4 over, which then gives me e to the 2x minus 3 is equal to 5/4. And to cancel my exponential, introduce a natural log to both sides, which then gives me, since the natural log and the e cancel out, that should just leave the exponent, 2x minus 3, equals my natural log of 5/4. Add 3. Gives me 2x is equal to the natural log of 5/4 plus my 3. Just to make sure that the 3 is outside, maybe I'll introduce a parenthesis to close that natural log. And then the last step would be to divide the 2 over. So my final result on this one would be whatever the natural log of 5/4 plus 3 is, if I divide it by 2. Now on to number 4. This one just wants us to sketch a graph. So if we look at what we have, I see addition inside of our function, and I see subtraction outside of our function. So the addition inside is going to move it to the left 3 places, whereas the minus 4 outside is going to move it down 4 places. And our parent function in this case is the y equals 2 to a power of x. So if it helps, we could make a t-chart for the 2 to a power of x with just -1, 0, 1, and 2. I might be able to fit one more on there, but that should be more than enough points. Negative 1 would be paired with 1 over the base, so 1 over 2. 0 is always paired with 1. 2 is paired with whatever the base is, and 2 is paired with whatever the base is squared. And if I think of the two things that are happening, if I go to the left 3, I should subtract 3 from x. And if I go down 4, I should subtract 4 from the y. And since those are the only two things I have to worry about, I can go ahead and make now a new t-chart with my actual function in this case that I'm trying to graph. Now we do also have a horizontal asymptote, may as well point out, of y equals 0, that now on this new one, because I'm shifting down 4 places, is now going to be at y equals negative 4. So I would personally always put that reference line on my grid first, so I know at least kind of how it's going to flatten out. Now as far as what is my new t-chart going to be, well, each of the x values I have are just going to become 3 less. So negative 1 take away 3 is negative 4, 0 take away 3 is negative 3, 1 take away 3 is negative 2, and 2 take away 3 is negative 1. Then it says to subtract 4 from y for this shifting down 4, so 1/2 take away 4 would be negative 3.5. Let's see, 1 take away 4 would be negative 3. 2 take away 4 would be negative 2, and 4 take away 4 is going to be 0. So it gives me enough points, hopefully, negative 4, negative 3.5 would be right about there. Negative 3 is just a little bit above it to the right. Negative 2, and negative 1, 0. So it seems to me like that is giving me enough points for me to be able to sketch a reasonable graph for this particular function. Moving on to now question 5. This one, notice it gives us a couple of formulas that we can use. We have one for compounding a set number of times, and we have a second one for compounding continuously. And it just essentially wants me to fill out this chart showing that I know how to plug in the numbers, I guess, that have been provided into the correct places. So it gives us that our p-value is 1,000, so as far as our general setup, it's going to be a equals 1,000 times 1 plus my rate. Well, my rate as a decimal would be 0.04, so it's going to be 0.04. Then it's going to be divided by the n, so since I have a different value of n that I'll plug in each time, I'm just going to keep this more in a formula format. And then the last part is to the n times t. Well, t it gives us to be 5 years, so I'll just call this 5n. So the first one would essentially just be plugging in a 1 in the two n's that I have. So if I go ahead and type that into the calculator, it gives me, if you give me just a second, a value of approximately 1,216 and about 65 cents. If I plug in a 2 in those same two spots where the n is supposed to be in our formula, this should come back, because I'm compounding more times, it should be a little bit more than the last result, which it is, 1,218 and 99 cents. Similar thing for 4. That gives me 1,220 and 19 cents. Do the same thing now with 12. Hopefully you kind of see what the pattern is here. And again, on a calculator you can kind of copy and paste and just change the one number that you need. In this case it comes out as 1,220 and 99.6, so actually we'll just call that $1,221, since 99 cents would round up on that one. And then the last one here with this formula is the plugging in of 365, where I see that in. And this one comes back 1,221 and 39 cents. And again, as that end value increased, notice that the end amount that I got increased. I guess I'll throw my pennies on that 12 one anyway. Now it's on to the last one. Continuously, remember, uses the PERT formula. So in this case, it would be 1,000 e to our rate 0.04 times our time 5. And if I go ahead and type that in as well, gives me a value of 1,221 and 40 cents. So just barely more than my daily, which with it only being 5 years, I didn't expect a whole lot of a change between those, but if that would have been maybe like 20 or 30 years, those numbers might be a little bit further off. But continuously in 365, especially in a short time frame, should kind of come back relatively close to each other. Moving on to question 6. This one now is more of a present value concept. In other words, how much should I invest? So we're actually going to be solving for P, which then means that this value down here of 12,000 must be the end amount. So it's going to be 12,000 is equal to, and it does say the phrase compounded continuously, so that's going to be the PERT formula. Had it said something like monthly or daily or anything along those lines, then I would have used the formula that had the 1 plus r over n from above. But with this one, we know that the principal, or the initial amount, is what we're trying to solve for. Our interest rate here, I'll go ahead and just rewrite that as a decimal, 0.065, by moving my decimal twice to the left. And it does say 3 years from now, so a t value of 3. So if I were to go ahead and look at how do I get the p by itself, well, ultimately I would just divide by that result of whatever 0.065 times 3 is as a power on e. And ultimately at this point now it turns into a calculator exercise. So if I type in 12,000 divided by that e to a power of 0.065 times 3, I get that the principal for this problem is going to be approximately 9,874, and it looks like about 2 cents if I were to round. So the fact that that came back less should be reasonable, because obviously if I invest a certain amount and I want it to turn into a higher number, or investment should turn into higher numbers, so had I got an answer that was, say, more than 12,000, that would be a little bit peculiar. Or if I would have got something that was super tiny, since 3 years is not really a lot of time, if I got an answer like in the 1,000 range, that would be another red flag of maybe I forgot to convert my decimal or my percent to a decimal for that particular problem. But this one seems reasonable, having 9,000 turn into 12,000 within 3 years, especially compounding continuously at a fairly high interest rate, seems at least reasonable. On to now question 7. This one is wanting us to determine what the half-life is. So a lot of times problems will give us a half-life. In this case, it's going to have us actually solve for it. So hopefully they gave me at least 2 bits of info here. So it does give me that when time is 0, I have 50 grams. And then it does give me another time of 7, I have 42 grams. So that should be enough for me to be able to follow. With this one would be the A equals, let's see if I can remember how your book wrote this or how we did it in the notes, CE to the KT. But again, it's an exponential decay model in this case, so I'm expecting the K value to come back negative. But ultimately I need to figure out what is my formula here from the 2 bits of info, and then use that to set it equal to when there's half as much left. So I'm going to eventually, the half-life, I'm going to use an end amount of 25 grams, since it said that I'm starting with 50 grams. But anyway, let's go ahead and kind of set up our formulas here. So I know that I have 50 as the initial amount, so when time is 0, that kind of tells me that the C in this case is 50, so that's good. And then I should be able to set it equal to the 42.031 when my time is 7 years. So it's going to be 7 times k up in that exponent area. So kind of similar to what we had to do with the earlier problem, just try and solve this expression. So first thing would be to divide that 50 over, which comes out as approximately 0.084062. I'm going to go ahead and just try and keep as many decimals as possible, just to try and maintain that accuracy. To cancel the e, I would introduce a natural log of both sides, and in this case I'd end up with 7k now would be left on the right is equal to just whatever that natural log is, which it did come back negative 0.174-ish. I'm going to go ahead and just try and keep it as exact as possible, again as long as possible. Divide the 7 over and get that my k value is equivalent to, and this time I'll actually go ahead and round it, a negative 0.02480. So I think if I go with 2.0248, that should be good. So now I've got the ability to try and figure out how long does it take for it to turn into 25. So it's going to be 25 is equal to the 50 times e to this k value I just solved for, times t. So this is the unknown. I'm trying to figure out how long is this actually going to take. So dividing the 50 over turns this into a 1/2. So the fact that it even gave me an initial amount really didn't matter for this part. Ultimately it's just going to turn into, just like we had to do before, introduce a natural log, so it'd be a natural log of this 1/2 that's going to equal that k times t. So dividing that negative 0.0248 over, should be able to give us our half-life for this problem of, I'm going to go ahead and kind of move that up into the middle here. My half-life, or my t, is going to be equivalent to, let's see, what is the natural log of 1/2 being divided by negative 0.0248. And it turns into a 27.95. So let's just go ahead and call that 27.95 years. I'll go ahead and label it, I guess, half-life. And if we think about, okay, it took 7 years for it to lose like 8 grams, and it's probably decaying even faster as we go. The fact that that came back relatively small like that, if we wanted to actually have the exact value, let's see what that would have turned into. So had we not rounded, it would have been 27.95. Wow. So rounding on this one, since it ended with a 0 after that 8, actually stayed relatively close. So that's not too terrible. But anyway, I got my half-life here of just a little bit under 28 years for that particular radioactive element, strontium-90. Alright, so now finally on to more of the calculus stuff on a calculus test. Hopefully that's reasonable. But now we'll actually go through and do some of our derivatives. So remember our basic formulas with our derivatives. In this case, are d over dx of some e to the u, where u is just some function of x, would be e to the u and then times u prime. Some other ones we might need to worry about would be like, what if the base was not e? So for example, a to the u. Ultimately what we would do is just multiply by the natural log of a, and then kind of follow the same pattern. So times a to the u times u prime. Let's see, derivatives of logs. So natural log of, say, some expression u is going to turn into u prime over u. And if we had some base that was not e, that was just equivalent to essentially u prime over a natural log of the base, then times u. So those are going to be like our four main things that we'll use throughout this. Still also intermixed with maybe some product quotient or chain rule type situations, but ultimately those formulas kind of take care of the chain for the most part. But anyway, let's go ahead and start jumping into some of these derivatives. So we've got y prime for this one. 4 is just a coefficient, so I'll let it just kind of hang out front. This is an e to the u, so I have to do e to the u times u prime, so it would be e to the x squared, but then times the derivative of the x squared, which is 2x. And I could probably rewrite that a little bit more clean and take the 2x and multiply it with a 4 in front, call that 8x, then e to the x squared afterwards. If I move on to now part B, this one I actually have a product, so I'll have to make sure I use product rule. And y prime in this case, let's go ahead and do the keep the first function, so x squared times the derivative of e to the x. Well, what's nice about that is it would be just an e to the x times a 1, so that stays e to the x. And then add that with, this time I'll do the derivative of the first function, 2x, and then times the original second function, e to the x. And look to see if there's anything I can maybe do. I could potentially factor this. Looks like they both have an x and they both have an e to the x. And if I were to take that out, that would leave me x plus 2 on the inside. So in the event that I did need to set this equal to 0, now having it in that factored form would be a little easier to find those solutions with. Moving on to part C, this one, notice we have division or a quotient, so I'll have to make sure to use a quotient rule. So it's going to be the low d high, so times the derivative of x, which is just 1, minus the high times the derivative of the bottom function. So e to the 2x is going to turn into an e to the 2x, but then times a 2 because of the derivative of 2x. Then all over the square of what's below, so e to the 2x quantity squared, which I'll be able to simplify here in the next step. Power to a power, remember we would multiply. So if we look at what's on top, it does appear that I do have an e to the 2x I could factor out. So let's go ahead and say that's an e to the 2x in front. And then I have a 1 that would be left on the first term minus, it looks like a 2x from the second term. Then it would be all over an e to the 2x being squared. The reason I'm going to leave it that way is one of those e to the 2x's actually would get to reduce with the one that's on top. So I can say that my final reduced version of this would be y prime equals 1 minus 2x over a plain e to the 2x. Now on to part D. This one now is one of the bases that's not equivalent to e. So remember with these, we just kind of start with what is the natural log of that base. So in this case, natural log of 3 is just going to be my coefficient in front. Then it's going to be follow the a to the u pattern, so it's going to be 3 to the 5x, but then times the derivative of 5x, which is 5. And so I could probably move that 5 all the way in front and just call this a 5 natural log of 3, all grouped, then times my 3 to the 5x, just so we can kind of see what the, I guess that would be a vertical stretch technically, if we were to think graphically about what's going on here. But again, that base of 3 is definitely separate from that 5 natural log of 3. And honestly, if we wanted to, we could figure out, by moving that 5 up as an exponent, we could figure out what 3 to the 5th is and have that be just the single number inside of the natural log. Ultimately, though, that doesn't necessarily make it that much easier, so I'm okay with you leaving it just like that. Now on to letter E. Now we're doing derivatives of a natural log. So remember, with natural log, it just turns into a u prime over u. So in this case, I'll figure out actually what the u prime is. So 3x squared's derivative would turn into just 6x, then over what's inside 3x squared. Looks like that actually can reduce. So I'll go ahead and divide the 6 by 3 and get a 2 on top. And x divided by x squared would just turn into a single x. So that one actually turned into something not too terrible. We also could have, if we really wanted to, we could have approached this where we separated that product into a sum, and then we could have then moved that 2 in front. And notice that then if I were to take the derivative of that, the derivative of the constant would have turned into 0 plus, and then 2 times the derivative of this natural log of x would have just been a 1 over x, which notice that would have also been able to turn into just a plain 2 over x like we just got before. So I don't know which way is easier for you to do, but by all means you can do both. The second one here, it looks like this one is one that I might want to go ahead and take the time to separate that out just to make things a little bit easier. So again, it's a product inside, so I should be able to make it a quotient, and I'm going to rewrite that radical as a 1/2 power. Move both of those exponents out front, so 2 natural log of x plus 1/2 natural log of x plus 1. And now that gives me something that should be a little easier to take derivatives of. The derivative of the natural log of x is just going to become a 1 over x, so I've got 2 times a 1 over x for this first part, added with a 1/2 times a 1 over x plus 1, and then the derivative of x plus 1 is just 1, so I don't need to multiply by any extra u prime. And so if I now look at what this would turn into, I've got 2 over x added with a 1 over 2x plus 1. And again, if I needed to do like a set equal to 0 step, I'd want to get common denominators. So I'm going to go ahead and multiply both of these by 2 and x plus 1 on top and bottom of this first one. And it looks like the second one just would have to get multiplied by x. And just kind of think in terms of what would I have in the numerator. So if I distributed this, it looks like a 4 through, I'd have 4x plus 1 more x from the other one, so that would give me a total of 5x. Then 4 times 1 would give me a positive 4 over my 2x and x plus 1. And that seems to me like a good stopping point. Doesn't really reduce any further, so I'll go ahead and leave it like that. But like I said, if I needed to identify critical numbers for this function, now it's not too terrible to set the top equal to 0 as well as the bottom, and potentially maybe set up a sign line and test my increasing and decreasing intervals if it was asking for like extreme of. But anyway, that's a follow-up question that we didn't really have to worry about doing with this problem. Moving on to the last 2 parts of this question 8. So now we've got a couple of logs that don't have a base of a. Remember, we do have the ability to use change of base formula if you would like, where we could switch it to natural logs. Remember, the base would go to the bottom, and I could treat that 1 over natural log of 3, since that's just a number, as if it were a coefficient in front of that natural log, so that way you don't necessarily have to memorize what the derivative is. Just remember your change of base formula and the fact that you can always switch it into natural log, so you only have to worry about remembering the natural log derivative formula. But anyway, let's go ahead and jump right on in. So I'll just leave that 1 over natural log of 3 as my coefficient in front. Then it's going to be times the derivative of the natural log of 2x minus 1, so that should be a u prime, which the u prime in this case would just be 2 over the u, which was 2x minus 1. And kind of combine those things together, I could say that the numerator is just a 2 over a natural log of 3. That's the coefficient in front of a 2x minus 1, and I don't have to necessarily distribute that out, because after all that would make it go from having to write natural log of 3 once to now writing it twice, so I feel like that actually is probably the best version to stop at. If we kind of follow suit with the next one, I can rewrite this also as a natural log of x squared minus 3x all over a natural log of 16, which then that 1 over natural log of 16, again, just like I did with the 1 over natural log of 3, I can just treat that like it's a coefficient, since that is just a number that I would get on my calculator anyway. So anyway, I've kept that in front. Now it's going to be the u prime over u for the natural log that's in the numerator. So the u prime of x squared minus 3x would be a 2x minus a 3 over the u prime, which is x squared minus 3x. And let's see, the top cannot really factor, the bottom I could factor an x out, but it would leave a x minus 3, which doesn't reduce with the top, so factoring that doesn't reduce anything, so I'm just going to go ahead and combine it together and just keep it in the format that we've got. So I've got natural log of 16, that's a coefficient in front of the x squared minus 3x in the denominator. And voila, there's my derivative for this one as well. Now, this one also could have had a separate route through. We could have technically factored, if we wanted to, the x squared minus 3x and turn that into, because it would be a product, we could turn it into a sum of 2 logarithms. I don't know if it necessarily makes the problem that much easier, but just wanted to point out that that is technically an option that you could do. Moving on to question 9. This one wants us to do some implicit differentiation. So we're trying to figure out what dy over dx is implicitly. So notice I've got essentially 3 different terms here. Fourth if you count the right side. Don't look like, or it doesn't look like I have any products or quotients, so I don't have to worry about those rules. It's just going to be individual derivatives, but anytime I take the derivative of something that has a y involved, I'll have to write the dy over dx. So x squared's derivative, that does not have y, so that's just going to be 2 times x, and then I guess technically if you wanted to say it would be times dx over dx, which equals 1. Then I've got minus 3 times a u prime over u for the natural log of y. Well, that would just be a 1 over y, but because that was the letter y, also times a dy over dx, or the derivative of y with respect to x. And then added with now the third term here, y squared will turn into 2y, but again also times a dy over dx, or a derivative of y with respect to x. And then my constant 10 on the right side, a very common mistake there is to leave that as 10. Remember, derivatives constant will always turn into 0. So now my focus shifts to, how do I get dy over dx by itself? Well, first thing would be to subtract any term that doesn't have dy over dx over to the other side. And now notice I've got 2 terms that both have dy over dx, so what I could do is just factor that out since the 2x now is gone. And that would leave me, it looks like a 3 over y plus a 2 times y being equal to the negative 2x. So for this one I might think common denominator, so multiply this one by y on top and bottom. So I can then picture, how do I get dy over dx by itself? Well, it would just be multiplied by the reciprocal, which would be, now that I have y as the denominator, a y over 3 plus 2y squared, it looks like, if I were to actually combine that, right? Because the numerator here is now a 2y squared. The denominator was y, so I could make that one single fraction. So if I multiply by its reciprocal, everything on top and bottom should be able to cancel out. And so now we can arrive at our final result here. Dy over dx is equivalent to this negative 2x times y in the numerator all over a 3 plus 2y squared in the denominator. And if I could reduce anything I would, but doesn't really look like I can factor anything out on the bottom, so there's really no reducing I can do. Alright, we're getting down to the nitty-gritty here. Last couple of problems to do. This one wants us to find an equation of a tangent line. So recall, with the equation of a tangent line, I need to know a slope and a point. It looks like they gave me the point part, so I've got that part taken care of. I just need to figure out what is my slope. Well, remember, slope will come from derivatives, so I need to figure out what is my y prime for this expression. Well, this is just going to be similar to what we had to do earlier. It's going to be a e to the u times u prime, so it's going to stay e to the x cubed, but then times the derivative of x cubed, which is a 3x squared. So if I maybe rewrite that in a little bit more, I guess, simple form, or just less likely to make a mistake form, I guess, maybe. Ultimately, I've got my slope equation to be this expression, 3x squared times that e to the x cubed. So now to find my slope at the point that they provided, -1 comma 1 over e, I'm just going to plug 1 in to that expression, and my slope would then turn into 3 times a -1 squared times e to a -1 cubed power. Well, -1 squared is 1, so that would just become 3 times 1, so 3 in front. And then e to a -1 cubed is just a -1, so I could rewrite that as a 3 over an e. So using point slope form, which recall is y minus the y1 equaling our slope times x minus the x1, I should be able to now plug in the points that they've given us. So y minus 1 over e is equal to the slope I just found, 3 over e, times x minus the x1, well, minus a -1 would switch to +1. So if I go ahead and try and get this into slope-intercept form, I would add the 1 over e over, not a 6 but an e, and distribute that 3 over e through, so that would give me y is equivalent to 3 over e times x, and that would be a 3 over e times 1 plus another 1 over e, so that would be a total of positive 4 over e, since those actually had a common denominator, which was convenient. And that would be the equation of my tangent line that passes through that point. Alright, finally on to our last question. Question 11 here wants us to identify all relative extrema as well as all points of inflection. So remember, extrema come from our first derivative, and when it equals 0, whereas points of inflection are going to come from second derivative, and when it equals 0. So let's just go ahead and dive on in, and let's figure out what our y prime is. So I do have a product, so I'll have to use product rule. So it'd be, let's do the, keep the first times the derivative of the second, which would be an e to the negative x, but then times a -1, added with, take the derivative of the first, which is just 1, and multiply that by the original second. So if I were to maybe simplify that, looks like I'd end up with, I'm going to write the positive one first, so I guess let's just write it this way, and then I'll show the switch of the order here in the next step. So -1 times x in front would be negative x, e to the negative x, added with an e to the negative x for that second term, which I could rewrite as an e to the negative x minus an x e to the negative x. That way that minus sign that's in front gets protected a little bit. And I could then, I guess, factor out that e to the negative x and see that this leaves a single 1 minus an x on the inside. So if I set that equal to 0, the solutions I would get would be x equals just positive 1, because e to the negative x never actually equals 0. So there's my critical number for my first derivative, and we could go through and actually just figure out on a sign line what we end up having. So let's see, if I plug into this e to the negative x times 1 minus x, if I plug in something like 0, I'd have an e to the negative x times a 1, or sorry, e to the 0, which is 1, times 1, which comes back positive, so that's going to be increasing going into 1. If I plug in a number like 10, something greater than 1, 1 take away 10 inside that parenthesis here would come back negative, and e to the negative 10, that would just be a positive value, so this part that's in front right here is always positive. It really is just coming down to what happens in the parenthesis. Since 1 take away 10 would come back negative, I'm expecting that to be a decreasing interval, so that means this would be a relative max, when the x value is 1. So let's go ahead and identify what that point is, since that was one of the parts of this problem. So it would be 1 comma, and whatever the function is at 1, well, that would just be a 1 times e to the negative 1, which really is a 1 over e. So there's my relative max for the problem. So I've at least established the first half of the problem. Second half wants us to identify also points of inflection. So let's go ahead and go back and try and figure out what is our y double prime. We could do this like a product rule with our factored version if we wanted to. So let's go ahead and do that. I'd end up with, let's do the keep the first function, e to the negative x, times the derivative of the 1 minus x, which would just be a negative 1. Then added with, let's do a keep the second function, 1 minus x, times the derivative of e to the negative x, which would be e to the negative x, but then times an extra negative 1. And if I look at what that turns into, I've got a negative e to the negative x. That's adding with a 1 minus x times a negative, so that would actually, let's see, what's the easiest way to write that? Let's go ahead and just move a negative out in front of that and make it an e to the negative x that's outside like that. So ultimately, if I need to now figure out what are the critical numbers, I would set this equal to 0. And if I wanted to do that, I could go ahead and add this e to the negative x over and get a negative parenthesis 1 minus x times e to the negative x, and it equals now a positive e to the negative x. To try and get this 1 minus x by itself, I could divide by both the negative and the e to the negative x, so both of those move. And why that's kind of nice is that gives me 1 minus x now all by itself is equal to a negative 1, because e to the negative x divided by an e to the negative x would be 1, but with the extra negative sign makes it stay a negative 1. Subtract the 1 over, I get that negative x would equal negative 2, which then gives me x should equal positive 2. And we could do a similar thing like we did with the other one and just plug in to our, I guess, second derivative here and just see what kind of number happens. Ultimately, the negative e to the negative x, if I were to plug in, I don't know, I guess let's just plug in 0 for that one. If I plug in a giant number for that, it's going to be really close to 0. Just thinking ahead, but ultimately if I plug in 0, I'd have a negative e to the 0, so negative 1 minus 1 minus 0, so 1 times 1. And if I have a negative 1 minus another 1, that's going to come back negative. If I plug in a number like maybe positive 10, negative e to the negative 10 would be super close to 0, minus 1 minus 10, so negative 9, times a number that's just a little bit positive, so it's going to be a super negative number minus a little bit larger negative number, and minus a negative would switch to addition, so that should come back positive. So that did have a switch, so that is a point of inflection. And since that's a point of inflection, I went from concave down to concave up. I can go ahead and say that there is a point of inflection with an x-coordinate of 2, and let's just figure out what is f of 2. Plugging back into the original, that would be 2 times e to the negative 2, which I could drop that to the denominator and make that e squared with a positive power. So 2 over e squared would be my y-coordinate for that same point. And if we wanted to figure out the decimal approximations of those, by all means we could, and compare it with what we see on a graphing calculator, but I'm okay with you leaving it in this exact format as well. That way you don't have to even worry about typing it into the calculator. But anyway, hopefully this has been helpful. Hopefully if there were any questions, this has addressed them, but as always, if you do have questions, feel free to let me know, and I'll see what I can do to make it make sense. Appreciate you guys taking the time watching this video, and we'll catch you next time.